towards the end of our last class, we had a brief discussion going on the two-block oscillator, right? If you recall this, on the two-block oscillator, we had these two masses, M1 and M2. We very slowly compressed it by an amount x naught or elongated it by an amount x naught and released the whole thing, preserving the center of mass. The center of mass was fixed here, didn't move. And then the two masses executed simple harmonic motion about the center of mass. The two masses executed simple harmonic motion about the center of mass. This was fixed as if this length was fixed. This was the natural length of the spring to which M1 was connected. This was the fixed length of the spring to which M2 was connected, the natural length to which M2 was connected, and the two masses M1 and M2 executed simple harmonic motion with omega equal to root k by mu, where mu was the reduced mass of the system, right? We also, from center of mass considerations, we also looked at how to find the amplitude of oscillation of the two masses, right? Now, one thing that I want to tell you before I proceed, in general, that's a very general remark, not related to the two-body system, but in general related to any 2 point particles, right? Any two particles, let's say M1 and M2, right? And let's say V1 is the velocity of this and V2 is the velocity of this. Then the center of mass has a velocity which is M1 V1 plus M2 V2 by M1 plus M2. That's the velocity of the center of mass, right? That's the velocity of the center of mass. Now, the two masses have a certain velocity as seen by the center of mass frame, right? For example, velocity of 1 as seen by the center of mass is going to be what? V1 minus VCM? V1 minus VCM, right? So which is going to be V1 minus M1 V1 plus M2 V2 divided by M1 plus M2? Yes or no? Right, then this M1 V1 will get cancelled with this M1 V1, and what you are left with is M2 into V1 minus V2 divided by M1 plus M2. Is it not? So that's a velocity of 1 as seen by the center of mass frame. Velocity of 1 in the center of mass frame. What's the velocity of 2 in the center of mass frame? It's going to be M1 by M1 plus M2 into V2 minus V1, right? That's going to be the velocity of 2 in the center of mass frame. Now, the kinetic energy of the system as seen in the center of mass frame, the kinetic energy of the system as seen in the center of mass frame is going to be kinetic energy as seen in the center of mass frame. Kinetic energy as seen in the center of mass frame is going to be half of M1 mod V1 Cm whole square plus half of M2 mod V2 Cm whole square, right? That's the kinetic energy in the center of mass frame. That's the kinetic energy of the system in the center of mass frame, which is going to be, as you can readily see, if I replace all of it, then half of M1 M2 by M1 plus M2 to mod V1 minus V2 whole square. You can check that out, right? But what's M1 M2 by M1 plus M2? Reduced mass of the system. And this is half mu magnitude of VREL squared. This is the relative velocity between the two particles. This is the relative velocity between the two particles. So mod of VREL squared. That's the kinetic energy of a two-particle system in the center of mass frame. It's a very important result. I do want you to understand this and take notice of this. The velocity, the kinetic energy of a two-particle system in the center of mass frame is going to be half of mu. Mu is the reduced mass of the system into magnitude of the relative velocity squared. Square of the relative velocity of the two constituent particles. Right? A very important result. Do remember this. Now, one more thing that I want you to just notice is that the velocity of the center of mass is given by m1 v1 plus m2 v2 plus mn vn. For a system of particles, the velocity of the center of mass is given by this, isn't it? Which means I could write this as m1 into v1 minus vcm plus m2 into v2 minus vcm plus mn into vn minus vcm equal to 0. Could I write it this way? Rearranging the terms. What is this? This is the linear momentum of m1 in the center of mass frame. This is the linear momentum of m2 in the center of mass frame. Linear momentum of mn in the center of mass frame, which really means that the linear momentum of a collection of particles in the center of mass frame will always be 0. The linear momentum in the center of mass frame of a collection of particles will always be 0. That's extremely important to understand, right? So linear momentum of a system as seen by the center of mass will always be 0. Clear? Now, let me get back to business. See, if I had a system of particles, let's say this is mass 2m. The spring initially in its natural state, this is mass 3m. This is the natural state of the spring, the two masses connected by a spring of force constant k, and say this mass at this instant is given an impulse v, and this mass is given an impulse such that this has a velocity v leftwards. Now, how would the system respond? This kind of a system is a little different from the earlier system, where when the spring was in its natural state, the center of mass was fixed. In this case, the center of mass is not fixed. Do you realize that the center of mass in this case has a velocity? The velocity of the center of mass in this case is 3mv minus 2mv, mv by 5, mv by 5m. So v by 5 is the velocity of the center of mass. Do you realize that? This is a system in which the velocity of the center of mass is v by 5. Now, how would this system respond? Let's understand how this system would respond. What would be really the kind of motion executed by 2m and 3m? Now, to put it very precisely, the way things will happen here is that in the center of mass frame, that means if you are an observer sitting upon the center of mass, then with respect to the center of mass, the two particles, 2m and 3m, will execute simple harmonic motion, will execute oscillation, and will execute oscillation with angular frequency omega equal to root k divided by the reduced mass of the system. In this case, the reduced mass of the system is 2m into 3m divided by 5m. 6m by 5 is the reduced mass of the system. Yes or no? m1, m2 by m1 plus m2, right? K is the force constant. So a center of mass will perceive the two masses to still execute simple harmonic motion with angular frequency equal to root k by mu. From the ground frame, however, things will be different. The system would bodily advance with a velocity of vcm, the center of mass representing translation of the system to the right. So it's as if the system moves in this direction. If you are sitting on the ground, you will see the following happen. This is how it's going to move. Just physically imagine this is how it would move. But if you are sitting on the center of mass, then this is what would happen. Pure oscillation from the center of mass perspective. In the ground frame, there would be translation as well as oscillation in the ground frame. That is how this system would physically respond. You know what I'm saying? Right? Now, let's look at the center of mass perspective, which is about the oscillation of the system. Let's look at the center of mass perspective, which is about, like I said, it will be pure oscillation from the center of mass frame. Let's understand exactly what's going to happen while you are sitting on the center of mass. Right? One thing for sure, observing everything from the center of mass, you will see pure oscillation of angular frequency omega, which is root k by mu. Now, in the center of mass frame, this is time t equal to 0. On the center of mass frame, then, let me look at the velocity of this with respect to the center of mass. Initial velocity when the spring is unstretched, the velocity of this in the center of mass frame is going to be v minus v by 5, which is 4v by 5 to the right. Now this is 3m. The mass 2m, realize, has a velocity v plus v by 5, that is 6v by 5 to the left as seen by the center of mass frame. How do you know if you have not made a calculation mistake? In the center of mass frame, check the total linear momentum of the system. 12 mv by 5 to the right, 12 mv by 5 to the left. Zero linear momentum in the center of mass frame, always cardinal, absolutely cardinal, right? Now, so this is the story of the two masses at this instant of time. Now, eventually, in the center of mass frame, the spring will elongate. The masses will move further. The elongation would result. Initially, the spring will elongate. After a while, what would be a state of maximum elongation for the spring? When the velocity of the two masses in the center of mass frame becomes 0. If the velocity of the two masses in the center of mass frame becomes 0, then the spring would have reached its maximum elongation, yes or no? And is it possible that in the center of mass frame, the velocity of one becomes 0 and the other one doesn't become 0? No, it's not possible. That means the velocities of the two masses in the center of mass frame should become 0 exactly at the same time, right? In the center of mass frame, the velocity of this becomes 0. In the center of mass frame, the velocity of this becomes 0. This then would be a state of maximum elongation, right? The velocity of this becomes 0 in the center of mass frame. The velocity of this becomes 0 in the center of mass frame. How about it? Right? Now, which means in the ground frame, what's the velocity of this? V by 5 to the right. What's the velocity of this in the ground frame? V by 5 to the right in the ground frame. But in the center of mass frame, this is this, right? Now, what's the maximum elongation thus produced? Question is, what's the maximum elongation? Okay, I can apply work energy theorem in the center of mass frame, right? In the center of mass frame, I apply work energy theorem. What's the kinetic energy of the system in the center of mass frame to begin with? Half mu into VREL squared. What is VREL? 2V. VREL is 2V, yes or no? What's the kinetic energy of the system in the center of mass frame? Half of mu. Mu is 6m by 5 into VREL squared means 2V squared. That's the kinetic energy in the center of mass frame, right? This becomes 0. In a state of maximum elongation, this becomes 0. So change in kinetic energy is minus of this, right? Where does it go? It goes towards potential energy of the system, which means if x max is the maximum elongation brought about, then this amount of change of kinetic energy reflects as change of elastic potential energy in the spring, applying work energy theorem with respect to the center of mass. So this is half k x max squared. Yes or no? Right? Sorry, this has VREL, whether I take with respect to center of mass or I take with respect to London or Patna or Paris, VREL will be the same. Do you realize that? Take VREL of this or take VREL of this, it's going to be the same. That's not going to change at all. Relative velocity will be the same, isn't it? Will relative velocity depend on the frame of reference? That's going to be the same, isn't it? Because VREL has, in that VCM has got cancelled, isn't it? So VREL is going to be the same. You look at this, it's still 2V, isn't it? Look at this, 2V. VREL will still be 2V. So I didn't bother too much about it, right? So this enables computation of the maximum elongation in the spring while the whole thing is still translating, right? Now, after this, what happens? After this, again, analyzing everything in the, yes, please. Yes, sit down. This will give me the displacement in the center of mass frame. For example, this particle, right? What's the displacement in the center of mass frame? The amplitude of motion of this, isn't it? From here to here, in the center of mass frame, it has moved by an amount equal to the amplitude. Now, what is the amplitude of this? The amplitude of this is going to be, this is the mean position for 3m because no forces are acting. V equal to A omega. Omega is known. So the amplitude of this can be known, yes or no, right? Now, once I know the amplitude, so in the center of mass frame, it has moved by an amount A, and then look at how much the center of mass is moved in that time. V by 5 into T. That time, I know, because from this position to this position is moving from the mean position to an extreme position, which is T by 4. Isn't it? Time period is 2 pi by omega, and here to here would be T by 4. Isn't it? T by 4. So in this time, the center of mass has moved by an amount V by 5 into T by 4, and this has moved by an amount A. So you add the two, that would be the displacement of this mass as seen in the ground frame. Right. Now, so far so good, right? All of it makes sense to all of you. Now, from this point onwards, what happens? Everything in the center of mass frame, because, see, reason I say it's best to deal with this in the center of mass frame, because I can convert all the velocities to the ground frame by accommodating this v by 5. See, at this point, I know the velocity of this in the ground frame, v by 5, v by 5. I know the velocity of this in the ground frame, because this was just this. Now, the spring starts to come back to its natural length, right? So, from this state, it will come back to this state of the spring, but what about the state of the two masses? Let's also understand what would be the state of the two masses, 2m and 3m, while the spring returns to its natural length. This was the natural length of the spring. In order to return to its natural length, what would be the state of the masses in terms of the center of mass? Let's examine that. Can I wipe this stuff? So, when it comes back to its natural length, the spring comes back to its natural length. Now, when the spring comes back to its natural length, the velocity of this in the center of mass would be 6v by 5 to the right, and the velocity of this in the center of mass frame would be 4v by 5 to the left in the center of mass frame. As seen by the center of mass, Yes or no? But as seen by a ground observer. As seen by, so this is the center of mass observer. This was the state of the two masses when the spring returned to its natural length, as seen by a center of mass observer. These are the velocities. But as seen by a ground observer, what would be the velocities of 2m and 3m? Okay. Velocity of this in the center of mass plus the velocity of the center of mass you'll have to add, isn't it? This was the relative velocity as seen by the center of mass. Add to it the velocity of the center of mass, you'll get the velocity of the particle in the ground frame. Yes or no? So it's going to be 6v by 5 plus v by 5, that is 7v by 5 would be the velocity of 2m in the ground frame. Now, yes or no? This is this is 4v by 5 to the left, center of mass is minus v by 5. So this would be in the ground frame 3v by 5 to the left. Right? So in the ground frame, the velocity of this is 3v by 5. Right? Now, obviously, in the center of mass, the spring will once again start to compress. So this was spring in its natural state, maximum elongation, coming back to its natural state, and now ready to compress. Again, while the spring compresses, the spring force will kill this velocity, will also kill this velocity in the center of mass frame. Right? In a state of maximum compression, the velocities of the two masses will simultaneously will become 0. The velocities of the two masses simultaneously become 0 in a state of maximum compression. The velocities of the two masses in the center of mass frame becomes 0. In the center of mass frame, it's going to become 0. That means, in the ground frame, what's the velocity of 2m? v by 5 to the right. What's the velocity of 3m? v by 5 to the right. So, both in a state of maximum and minimum compression, a ground observer will report on the two masses the same velocity. Yes or no? Right? So now, this is, you must have a very clear idea of what's happening in the center of mass frame. If you want to look at everything from the ground frame, then superimpose whatever is happening in the center of mass frame to what's happening to the center of mass. The center of mass would have moved by an amount in a time equal to 5 seconds. The center of mass would have moved by an amount v by 5 into 5 to the right. And you might want to superimpose that to the oscillation that is brought about. Now, the important thing is, one thing, I told you, you can calculate the maximum compression and the maximum elongation with the help of half mu v rel square is half kx max square, applying work energy theorem in the center of mass frame. The other thing that you could do is, look, let me start with the system ab initio. You know what I started with on the system, but so far so good, right? You're all in tune with me. What we started with was the following. In the ground frame, this is what we started with. The center of mass having a velocity v by 5. Right? This is just another perspective to this. It could just be a substitute to whatever I have told you. Something that you might want to use at some point of time. It's important that you at least understand what I'm saying. It's easy though. Now, in this state, what's the total kinetic energy of the system that we started with? The spring was in its natural state. What was the total kinetic energy of the system? Let me call it E total. E total. In the ground frame. And now everything in the ground frame, right? Half of 2m into v squared plus half of 3m into v squared. That's the total kinetic energy of the system. Total energy of the system, so to say, right? Now, what we can say is the total translational energy, if someone has to say, that means out of this E total, actually, this total energy has two constituents. One is energy of oscillation, the other one is energy of translation. There is that energy of oscillation in this E total, and then there is that energy of translation. The energy of translation, we might want to imagine. Energy of translation. The energy of translation we might want to imagine as half of 5m into v by 5 square. That's the energy of translation. The oscillation energy would be the difference of these two. The oscillation energy would be the difference of these two. Energy of oscillation is E total minus E translation, which you can calculate. And when the spring is in its maximum compressed state, this would appear as half kx max squared. This would appear as half kx max squared, this energy of oscillation. That will also enable you to calculate the maximum compression or the maximum elongation that could be brought about in the spring. Got me? Now, so far so good, right? Not a problem. Let me know if I could wipe this off. So you precisely understand what's happening in the center of mass frame. And it's best that we analyze the system in the center of mass frame in view of the fact that, eventually we could map it back to the ground frame with the factor v by 5 for this, for example, with the velocity of the center of mass available to us, we could convert it back to the ground frame as and when we want. So initially might as well just work around the center of mass frame so that it reduces to pure simple harmonic motion of the two masses, and the regular system that we have studied, the the regular two-body oscillation that we looked into in our last class. Now, let me vary this a little bit. But so far so good, right? You're absolutely clear about whatever I've said. Huh? Let me change the situation a little bit. Can I wipe this off? Huh? Let's say there are two masses, M1 and M2. The spring in its natural state, and the two masses at rest, initially. And I apply a force F. A constant force F on mass M1. I apply a constant force F on mass M1. I now want to figure out the maximum and minimum elongation in the spring. Maximum and minimum elongation in the spring I want to figure out. Okay, now this kind of a system, once again, I'll analyze in the center of mass frame, which is an accelerated frame. In this case, realize that the center of mass is accelerated. Yes or no? This is the center of mass. The acceleration of the center of mass, as you would witness, is F by M1 plus M2. That's the acceleration of the center of mass. Yes or no? Right? If the center of mass is accelerated, then on the two masses there would be a pseudo force acting. Right? There would be a pseudo force acting on the two masses in the center of mass frame, which is an accelerated frame. So there is going to be a pseudo force on this mass M1 ACM this way, right? And on this mass the pseudo force is M2 AC. It's the pseudo force on this mass. Let's say in a certain time, M1 gets displaced by an amount x1 to the right and M2 gets displaced by an amount or x2 to the left. M1 gets displaced by an amount x1 to the right, M2 gets displaced by an amount x2 to the left. And let's say this is the state where the spring has either the maximum elongation or the minimum elongation. Now, one fact which should have dawned upon you by this time is that in a state of maximum or minimum elongation, the velocities of the masses at the ends must be the same. You know what I'm saying? In a state of maximum compression or minimum compression, always maximum elongation or minimum elongation, the velocities of the two masses must be the same at that point. That's very important. In all these cases, this will always happen. The velocities of the two connectors at the end must be the same in a state of maximum or minimum elongation. So let's say in a state of maximum or minimum elongation, this is advanced by an amount x1 to the right and this is moved by an amount x2 to the left, right? And when that happens, if the velocity of this is v at that instant, then the velocity of this will also be v to the right, would also be v to the right. They must have the same velocity at an instant of maximum and minimum elongation, and all of it in this ground frame of reference, all of it in the ground frame of what's the confusion? In this case, momentum is not conserved because there is an external force acting. So momentum is not conserved in this case. External force, it's adding momentum to the system, right? So in a state of maximum or minimum elongation, the velocities of the two masses must be the same, right? Now let me apply work energy theorem in the center of mass frame. Let me apply work energy theorem in the center of mass frame. Work energy theorem in the center of mass frame. Let's do that. Now work done by F is going to be F into x1, right? Is it not? F into x1 is the work done by F. Work done by this unit of force would be minus m1 ACM into x1, right? Work done by this is going to be m2 ACM into x2. x2 has been the displacement to the left, same as the direction of m2 ACM. So work done by the second unit of force is going to be m2 ACM x2. Right? And this must be change of kinetic energy of the system in the center of mass frame. We started with rest. So kinetic energy in the center of mass initially was 0. And in this state, in a state of maximum or minimum elongation, VREL is 0. So kinetic energy in the center of mass frame once again is 0. Right? So change in kinetic energy in the center of mass is 0. Right? Yes or no? Work done by, and there is also work done by the spring force. There is work done by the spring force, which is half k x1 plus x2 whole square. That's a change in potential. Work done by all forces, real and pseudo, must be change in kinetic energy plus change of potential energy of the spring. This is change of potential energy of the spring, half k into x1 plus x2 whole square. Does it make sense to you? Where x1 plus x2 is the elongation, maximum as well as minimum, right? So if you end up getting two values of x1 plus x2, one must be the maximum elongation, the other one must be the minimum elongation. Both these subscribe to the same physical condition of the two masses acquiring the same velocities in a state of maximum or minimum elongation. Now, I can replace this ACM by F by m1 plus m2. So this gives me fx1 into m2 by m1 plus m2 plus fx2 into m2 by m1 plus m2 equals half k x1 plus x2 whole square. Right? Which gives me once again fm2 by m1 plus m2. See, fm2 by m1 plus m2 into x1 plus x2 is half k x1 plus x2 whole square. Two values of x1 plus x2 you get. One is 0, isn't it? One of the values of x1 plus x2 is 0. That means the minimum elongation is 0. Minimum elongation is 0. That means the spring is never getting compressed. The spring in this case is never getting compressed. So the minimum elongation is 0. The maximum, the other value of x1 plus x2 gives me the maximum elongation. The other value of x1 plus x2 is how much? Is 2f m2 by m1 plus m2 into k. That's the other value of x1 plus x2. 2f m2 by m1 plus m2 by k. That must be the maximum elongation produced in the spring. That must be the maximum elongation produced in the spring. Got me? F is acting on M1. So pseudo force, I have taken that, and F still acting on M1. F is still acting on M1. It's not acting on the center of mass, it's acting on M1. Its impact could be realized with the center of mass, but otherwise it's a real force acting on M1. The work done by this force will still be this. So now, can I wipe this off? Now to just tell you another, some relevant variations around these two block systems. One very common variation for this two block system this case of a truck let's say truck of mass M1, mass M2. And I compress the spring a little bit. I push this mass so that either the spring gets compressed or elongated. Let's see what happens to the motion of M1. Let's examine what would happen to the motion of M1 in the ground frame. In the ground frame. Let's see what happens. So in the ground frame, let's say when this moves by an amount x2 as seen by the ground observer, then do you realize that there are no external forces acting on the system? Then M1 must move to the right to preserve the position of the center of mass of the system. M1 moves by an amount x1 to the right so that the center of mass of the system is preserved at the same spot in a manner that M1 x1 must be equal to M2 x2. Yes or no? No. If this was with respect to the cart, then it would have been M1 plus M2. See the earlier raft problem, the distance moved on the raft was with respect to the raft, not as seen on the ground frame. Right? So this is as seen by the ground observer. X2 moves left, M2 moves x2 units to the left, M1 moves x1 units to the right in the ground frame. If this was with respect to the cart, then what you said would have been right. Right? Then it would have been M2 x2 equals M1 plus M2 x1. If this was x2 with respect to the cart. Go back to the raft problem that I dealt with earlier. So that was distance moved on the raft. L was the distance moved on the raft, means with respect to the raft. This was distance moved by M2 as seen by the ground frame. That's the difference. Huh? Please make sure you understand this. Now, by what amount has the spring got compressed? x1 plus x, isn't it? The spring then would have got compressed by an amount x1 plus x2. Yes or no? And therefore the force of the mass M2 is going to be k into x1 plus x2 to the right. Restoring force. This is the restoring force, isn't it, on the mass M2? K into x1 plus x2. So restoring force on M2 is of magnitude k into x1 plus x2, where x1 is the displacement of m2 with respect to its mean position. This was the equilibrium position of m2, right? This could be written as k into x2 plus x1, which is m2 x2 by m1. Yes or no? Right? Which is the same as k by m1 into m1 plus m2 into x2. That's a restoring force proportional to the displacement from the mean position. So the motion of m2 must be simple harmonic, right? With the equivalent force constant for the system being this. The omega of oscillation then would be root k of the system m1 plus m2 by m1 m2, which is root k by mu. Root k by mu. This again is identical to the regular two-body oscillator that we've studied. Does it make sense to all of you? Yes. Yes. I mean, if you really think about it physically, I mean, you could unfold this mass m1 and bring it here, and it will resemble the two-block oscillator. I mean, just imagine this two. Open up and bring this mass m1. There is no physical difference between this situation and that situation, isn't it? That's the way we can look at it. Say there was a mass m, a spring of force constant k, mass 2m, at rest on a smooth, harmless surface. And I gave this an impulse j. I imparted an impulse j to the mass m. Right? I imparted an impulse j to the mass m. The mass m will develop a velocity when? The mass m develops a velocity which would be j by m. Yes or no? Would be j by m. The velocity of this will still remain 0. Right? The center of mass will feel the heat of j. The center of mass will develop a velocity which would be j by 3. That's the velocity of the center of mass. So now what would happen? There would be translation as well as oscillation. There would be translation as well as oscillation, right? Like before, it would reduce to a system that we've already investigated. And the omega of oscillation would be root k divided by mu. Use the reduced mass of the system, m into 2m divided by 3m. m into 2m divided by 3m would be the reduced mass of this system, right? What then? In the center of mass frame, what then would be the amplitude of oscillation of this? If this is the velocity of this mass in the mean position, if A is the amplitude, then this would be A omega. Omega known, so you would know the amplitude of oscillation of small m. You would then know the amplitude of oscillation of small m. Got me? Sometimes they would give you mass m1 another mass m2, spring of force constant k1, spring of force constant k2, right? And you would bring the two masses closer together and release. You would bring the two masses closer together and release. Realize that essentially when you compress it by a certain amount x, this will elongate by that much amount. So the force that would act on the two masses would be actually k1 plus k2 into x, right? So essentially this could be reduced to m1, m2 with the two springs being like this, k1 and k2. Will it not get reduced to this? Because even in this, say if I compress it by an amount x, then the restoring force would be k1, the outward force would be, the force in the spring would be k1 plus k2 into x. Same with this, isn't it? So this could be reduced to this. So these are like k1 and k2 in parallel. So this would become k1 plus k2. So it's like a two-body oscillator, m1 and m2 with a k equal to k1 plus k2. It will execute simple harmonic motion with omega equal to root k by reduced mass m1 m2 by m1 plus m2. Right? It makes sense to all of you? Now having said this, let me illustrate a few more things from the JEE which I think are pretty relevant. Fixed inclined plane, theta, this is a cylinder of mass m, radius r, let's say, attached to the spring AB. If the center of the cylinder is moved 10 millimeters downwards, determine the period of oscillation, the maximum velocity of the cylinder, etc. Now, two approaches to this. Let me first take the energy approach to this problem. Let me first take an energy approach to this problem. The energy approach is, let's say, when the cylinder at some instant during its course of motion descends by an amount x. Let's say the cylinder descends by an amount x. During the course of its motion, let's say the cylinder descends by an amount x. And when it has descended by an amount x, now in this case realize that there is ample friction here, so that the cylinder only rolls. And if the cylinder only rolls, the work done by friction will always be, it will not interfere with the total energy of the system, right? Therefore, the prospect of producing simple harmonic motion out of it is fair, right? That could happen. Now, at a certain instant when the cylinder has moved down, the center of mass of the cylinder has descended by an amount x. Let's say V is the velocity of the center of mass of the cylinder. Let's say V is the velocity of the center of mass of the cylinder. And omega is the angular velocity of the cylinder, right? Because it's rolling. So if there is a V, there would be an omega such that V would be R. Now, since it's in a state of pure rolling, the total kinetic energy of the cylinder is as if it's in a state of pure rotation above the point of contact. Yes or no? This is the instantaneous center then. It's in a state of pure rotation about the point of contact, right? So that means the total energy of this, the total kinetic energy of this would be half of I about the point of contact into omega squared. That's the kinetic energy of the cylinder. So half of I about the point of contact. I about the center of mass is mr squared by 2 plus mr squared. So 3 by 2 mr squared about the point of contact parallel axis theorem. I about this is half mr squared plus mr squared. That's going to be 3 by 2 mr squared about the point of contact, moment of inertia. Into omega squared. Right? That's a kinetic energy. Now, if it has descended by an amount x, A to C. This is theta, this is x. That means its vertical fall has been x sine theta. Its vertical fall has been x sine theta. Therefore, the potential energy expression is minus mg x sine theta. The spring has got elongated by an amount x, so the potential energy in the spring is half kx squared. This is the energy of this spring cylinder system. That's the energy of the spring cylinder system, and it's not going to change with time. Total energy is constant. Friction is not doing any work because it's in a state of pure rolling. Now, again, since it's rolling without slipping, can I also say that V is R omega? So R square omega squared is actually V squared. R square omega squared is actually V squared. dE dt must be 0. Which gives me 3 by 2 mv dV dt minus mg sine theta dx dt. Dx dt is V plus kx dx dt, which is V. This must be 0. How about it? Which means 3 by 2 dV dt, which is the acceleration, must be g sine theta minus kx acceleration, then dV dt is 2 by 3 g sine theta minus 2k by 3 x. And then do you realize that this must be omega square? This must be omega square. Omega then would be root 2k by 3m. That must be the angular frequency of rotation. This, however, this omega is different from the angular velocity. This is, let me call it omega naught, angular frequency. It's not the angular velocity of the cylinder. It's not the angular velocity of the cylinder. This is the angular frequency of oscillation of the center of mass, angular frequency of oscillation of the center of mass. right? Just to tell you one thing where I goofed up, there was these masses that I missed all over the place. So when I divided by m, this m I had missed. So then this is the angular frequency. Now the same thing, let's analyze with the help of torques, restoring torque on this. See, there was, eventually this reached an equilibrium position. From the equilibrium position, let's see what happens when we displace it further by an amount x from the equilibrium position. This is the equilibrium position of the cylinder when the net of all forces and all torques on the cylinder was 0. The spring obviously was elongated in this state. The spring was already elongated, and the forces acting were the spring force, static friction, mg cos theta, mg sin theta, normal reaction, etc. And mg sin theta, spring force, frictional force together produce equilibrium, both translational as well as rotational. Now, from the equilibrium position, imagine theta, that the center of mass was slowly displaced by an amount x parallel to the plane, right? Now, in the process, this must have rotated, let's say, by an amount beta. The cylinder must have rotated by an amount beta, where in order that it was rolling all the time, the displacement of the center of mass must have been r times beta, right? Now, the additional spring force, everything else is remaining the same, mg cos theta, mg sin theta, normal reaction. What is the only thing that is changing? The spring force, right? Now the additional spring force is kx to the right, that means upwards. The additional spring force is kx upwards. There was already a spring force, but this is the additional spring force, that's going to be kx upwards. This additional spring force about the point of contact, which is also the instantaneous center, the additional spring force produces a torque which is kx into r about the point of contact. Now, this then must be the restoring torque, because this has rotated beta this way, whereas the torque about the point of contact that kx produces is this way. So this must be restoring in character, right? So I put a minus sign, and this must be I about the point of contact into angular acceleration. So I about the point of contact is 3 by 2 mr squared into alpha, which is d2 beta dt2. Yes or no? Now all that you need to do is replace x by r beta. So that gives us d2 beta dt2 beta. This then must be the omega square. Omega then must be root 2k by 3m. This must be the angular frequency of oscillation of the center of mass, right? Now, again, what about the amplitude? What about the amplitude? Amplitude would be given by us. If it was originally in equilibrium position and if I pulled it down by an amount 1 centimeter, then that would be the amplitude of oscillation of the center of mass, right? What would be the velocity at the mean position? The velocity at the mean position would be omega times the amplitude. That would be the velocity at the mean position, omega times A, right? A similar situation. Look at 7. Solid cylinder. Cylinder rolls. And we want to find the period of oscillation of the cylinder. We want to find the period of oscillation of the cylinder. Now, so if it's rolling, that means if at some instant it has translated by an amount x, then it would have rotated by an amount theta such that x will be r theta, because it's rolling, right? It would have rotated by an amount theta such that theta would be x by r. Initially the springs unstretched, so this is the equilibrium position. This is the equilibrium position. Now, when I cause the center of this to move by an amount x, the topmost point will move by an amount 2x. Why? Because the velocity of the topmost point in pure rolling is twice the velocity of the center of mass. Yes or no? Right. So while this moves by an amount x, the topmost point moves to the right by an amount 2x. So while this spring elongates by an amount x, the spring will compress by an amount. Spring will compress by an amount 2x. Right? And if it has moved to the right, then theta has been in this sense, theta has been in this sense, clockwise sense. However, and there has been frictional force also. So now I can take torque about the point of contact. I can take torque about the point of contact. Now, what's the torque of this spring about this point? K2 into 2x into 2r. Yes or no? What about the torque of K1? If this moves to the right, then this is the sense of torque that this exerts. If this elongates and it's on this side, then same sense, opposite to theta. See, this is elongating. So spring force is like this. So about the point of contact, the sense of the torque is still opposing theta. I'll explain again here. So both this spring and this spring are opposing theta, So the restoring torque by the spring connected to P is this. The restoring torque by this spring about the point of contact is K1x into R. That's a restoring torque. So which is like 4k2 plus k1 into r into x, and that must be I about the point of contact, which is 3 by 2 mr squared into angular acceleration, which is d2 theta dt2, and now a minus sign because it's a restoring torque, right? And this x I can write as r theta, this x I can write as r theta. This r square will get cancelled. So do you realize that omega squared is 4k2 plus k1 into 2 by 3m? That's omega squared. Omega then would be square root of this. Omega then would be square root of this. The angular frequency. It executes simple harmonic. Let me also do it from energy principles so that you have a mental comprehension of what's happening. You understand this from first principles? We found out the restoring torque, tau equal to I alpha, etc. Right? Now, from energy principles, let's look at it from energy principles. Hoping that you've understood what I have communicated, right? Say at an instant when this has moved to the right by an amount x, let's say it develops a velocity v. It develops a velocity v. What's the total energy? And it develops an angular velocity omega. This develops an angular velocity omega, which is different from the angular frequency, V, however, would be r omega. Now, if this has a velocity v, then it's in a state of pure rotation. Therefore, the total kinetic energy would be as if it's in a state of pure rotation about the point of contact, the instantaneous center. So the total kinetic energy of this would be half of I cylinder, so 3 by 2 mr squared into omega squared, right? Then this suppresses by an amount 2x. So the potential energy of this is going to be half k2 into 2x whole square. This elongates by an amount x, so half k1 into x squared. And this r square omega squared I can write as v squared. This r squared omega squared I can write as v squared. And then all that you need to do is dE dt equal to 0, and you will get dV dt proportional to x with a minus sign, and that constant of proportionality would be the angular frequency of oscillation of the oscillator. This is the energy perspective to the same problem. Got me? Now, let's quickly go through the first few problems. All's fine so far, right? Solid sphere? Huh? Okay. You might attempt, both energy and torque we can do that, but if you like, at the end we'll discuss. Okay? You at least have this attempted properly, then I'll discuss that. Alright. So originally this was executing simple harmonic motion with mean position 10, isn't it? Because it will be 10 plus 3, 3 to the right of 10 and 3 to the left of 10. That's a simple harmonic motion that this was executing. X equal to 10 was the mean position. Do you realize that? It can go 3 units to the right and 3 units to the left. The omega of the oscillator was 10 then, sine omega t. So the omega of this oscillation was 10, right? But omega is root k by m. So k must have been 100. The force constant must have been 100. Yes or no? The force constant of the oscillator of the spring must have been 100. Now, while this was at the mean position, this was moving with a velocity, let's say, omega times the amplitude. The amplitude of motion was 3 units, isn't it? The amplitude of motion was 3 units. And this comes here and collides elastically with this. These are two identical masses in a state of head-on collision. What would happen? They will exchange velocities. They will exchange velocities. That means after this strikes this will move to the right with a velocity omega a. This will move to the left with a velocity 0.6 meters per second. Yes or no? This is 1 kg. It starts moving to the left with a velocity of 0.6 meters per second in the negative x direction. Right? And it's at x equal to 10. At, let's say time t equal to 0. At time t equal to 0, it's at x equal to 10. Now, this, so, what would happen to omega after this collision? It will not change because k has not changed, mass has not changed. Omega will remain 10 radians per second, right? What about the amplitude of motion? Will that change? Yes, that will change. Because now, this is still the mean position. Why is this the mean position? Because no net force acting at this position, right? So what if the direction of velocity has changed? No net velocity, no net force acting at this point. So this V must be the omega, which is 10 into amplitude, new amplitude A. That means the new amplitude is 0.06 meters. Is 0.06 meters. So the new amplitude A is 6 centimeters. That's a new amplitude. 6 centimeters is the new amplitude. A prime. The original amplitude was 3 centimeters. The original amplitude was 3 centimeters now. At time t equal to 0, it's still at x equal to 10, but its direction of velocity, instead of being 30 centimeters per second to the right, it's 0.6 centimeters meters per second to the left. Yes or no? That means 60 centimeters per second to the left is its velocity, which means the x versus time. At time t equal to 0, x is still 10. They will still be, now instead of 3, you will have 6 centimeters as the amplitude. 6 sine, and this will still remain 10, right? Now this will be minus. Why? Because the velocity at time t equal to 0 is minus 0.6. So if I differentiate x 10 minus 6 sine 10t, then the velocity at time t equal to 0 would be minus 60 centimeters per second, which is what it should be at time t equal to 0, right? So instead of being 10 plus 6 sine 10t, it will be 10 minus 6 sine 10t, so that the velocity of 6 meters per second to 0.6 meters per second could be realized to the left. Got me? So this is the new displacement time characteristics for the oscillator, right? Now, can I wipe this off? Okay, this was a pair of masses connected by a natural spring. This mass comes and strikes us. Two identical masses, perfectly inelastic collision. To conserve momentum, well, this will become 2m, velocity of this will become v naught by 2 after collision. Yes or no? So this is just before collision. Just after collision, yes. Huh? Will? Collision occurs only between them. The spring, two things. One, the spring is in its natural state, so there is no spring force. One thing. The spring is still at the collision occurs for such a short time that in that period, the spring doesn't get compressed, right? So spring force is 0. So 1. No, I have another point to make here. Even if the spring force existed, we could still conserve linear momentum because of two things. One, the spring is a non-impulsive element. It's incapable of acting that fast. 1. 2, the forces of collision are much larger than the spring force. So the change in linear momentum, the small change in linear momentum in that short time that the spring force would have brought about would be really small compared to the momentum redistribution brought about by colliding forces. So we can ignore the effect of spring force, like when there is a particle falling vertically, another particle moving up, when they undergo a collision, we still apply conservation of linear momentum. Reason being because, yes, there is a gravitational force, but the impulse of gravity is small compared to the impulse of the colliding forces, so we ignore that effect, right? Okay, so now when A and C collide, they coagulate to produce mass 2m and a velocity v naught by 2 commensurate with conservation of linear momentum. This then is the system. The velocity of the center of mass, then this will be at rest, right, initially, and the velocity of the center of mass would be mv naught by 3m v naught by 3. v naught by 3 would be the velocity of the center of mass. Acha, theek hai. Look at this. What's the total momentum that this brings to the system? mv naught, and it will reflect in the center of mass. The total linear momentum, the center of mass, could be used as a representative to reflect the total linear momentum of the system unconditionally. So then this is going to be the total mass of the system, 3m into vcm. So vcm would be v naught by 3. Do you realize that? vcm would be v naught by 3. Now, what's the total kinetic energy of the system? Half of 2m into v naught by 2 whole squared. That's the total kinetic energy of the system to begin with, right? There is an energy of translation which is built into the center of mass. So that's going to be half of 3m into v naught by 3 whole square. Why is this different from this? Because there is oscillation energy. The difference is the oscillation energy. E oscillation is E total minus E translation. E total minus E translation, right? And E total minus E translation, this oscillation energy in a state when the spring is completely compressed or completely elongated, when the two masses are brought to rest, It will reflect as elastic potential energy in the spring. In a state of maximum compression or maximum elongation, it will reflect as elastic potential energy of the spring. So this must be half K x max squared. So that's one way to calculate x max. The other way we could have calculated x max was, look at this. Spring not elongated. The kinetic energy in the center of mass frame, is half of mu. Mu is 2m into m by 3m. 2m by 3 is mu. Into vrel squared. Vrel is v0 by 2 whole square. Because this has zero velocity. So v0 by 2 whole square is vrel in the center of mass frame. When the spring is in a state of maximum compression or maximum elongation, the entire kinetic energy in the center of mass frame will appear as half k x squared. So that's another way you could have calculated the maximum compression in the spring. The maximum compression in the spring could also have been calculated this way. And all of this, one thing you must realize here is, if there are no external forces acting on the system, you could have gone from first principles, even without knowing anything that I have covered, as long as you can apply your work energy theorem properly, as long as you realize that there is conservation of linear momentum always. See, we started with mv naught, it's always mv naught, no matter what the state of the spring is. The total linear momentum of the system will still be the same, even in the ground frame, right? And in the center of mass frame, it will be the same and will be equal to if there are no external forces. So even if you keep track of the rudiments, you'll be doing fine with all of this, right? Even if you didn't know anything that I have taught, right? You could still be doing good with things. Now, of course, the omega would be root k by mu, etc., which I have already told you. The omega of oscillation of the two masses would be root k by mu. Mu is the reduced mass for the system, etc., right? So these were the various parts. There are times you want to look at things a little differently, in the sense see, can I wipe this off? There was a block of mass m, spring of force constant k. This end was a and was given a velocity v. And we want to find the maximum extension in the spring. We want to find the maximum extension in the spring. Now, in a situation of this kind, obviously the spring will elongate. The spring will elongate because this end has zero velocity, this has velocity v. The spring will elongate now, right? But this will also move to the right over a period of time, because while the spring elongates, while this end moves to the right, the spring elongates. There are forces developed in the spring which will cause m to move to the right. Yes or no? Now, a situation of this kind would be better dealt with if you imagine the following. Imagine an observer like this, O, moving with A with a constant velocity v. The observer moving along with A with a constant velocity v. Now, in a frame of reference attached to O, this will move in this direction. This will move in this direction with a velocity v at this instant of time. Yes or no? At this instant of time, t equal to 0. Right? And the velocity of A as seen by the observer, will be 0 at all times. Right? So it's as if A is fixed as seen by this observer, and this has started to move to the left with a velocity v. So now look at things from this observer's perspective. This is fixed and this is imparted an impulse giving it a velocity v to the left. So if this starts moving to the left, then it will get retarded as seen by this observer. Then in a state of maximum elongation of the spring, the velocity of this will become 0. That means it would have lost all its kinetic energy as half k x max squared. That will give you the maximum elongation in the spring. Do you understand? Yes. I'm saying, look at an observer moving along with A with a velocity v to the right. So, let's say time t equal to 0, and in fact then at all times A is a fixed point as seen by this observer, right? And at this instant he finds that m moves to the left with a velocity v as seen by this observer, isn't it? Which means it's as if this is equivalent to a situation where A is fixed and this is given a velocity v to the right. So the spring will elongate. Eventually a state of maximum elongation of the spring would be 1 when the velocity of this will become 0. That means it would have lost kinetic energy equal to half mv squared. And where would it have appeared? It would have appeared as half k x max squared as elastic potential energy in the spring. That is how it would have happened. Got me? Right? Now there is a little bit of a wonky spring. F is minus kx for k greater than 0 and is minus 2kx when x is less than 0. We want to find the time period of motion. Number 4. For a spring whose force constant is k when it's to the right of the origin and is 2k when it's to the left of the origin, we want to find the time period of motion of this, right? So x equal to 0 is still the mean position. Right, because f is 0 at x equal to 0. To the right of 0, it's being acted upon by a force equal to kx. To the left of x equal to 0, it's being acted upon by a force 2kx directed towards O. Which means, now, when it goes from O to A is the rightmost extreme. Let's say A1 is the rightmost extreme. When it goes from O to A1, the rightmost extreme, the omega that it has would be root k by m. The time period that it has is 2 pi root m by k. Right? Now the time it takes, let me call it T1. The time it takes to go from O to A1 and then A1 to O is going to be T by 2. So T1 by 2. Right? Now, let's say its leftmost extreme is A2. When its leftmost extreme is A2, then the omega 2 for this motion from O to A2, the omega for this motion is going to be root 2k by m. The time period for this part of the journey is going to be 2 pi by omega 2 pi root m by 2k. Now, the time it takes to go from A2 and then come back to O is going to be T2 by 2. That means this is the time it takes to go from O to A1 to A2 and then back to O. This is a full cycle. This is a full cycle, and therefore this must be the time period of motion for this oscillator. This must be the time period of motion for the oscillator, right? Yes or no? Now, the rightmost, so then, well, it has its amplitude to the right is A. That's given. A is its amplitude to the right. We want to find its amplitude to the left. That means its leftmost displacement from the origin is what we want to find. One thing, the total energy is not going to change. The total energy is still half Ka squared. And this must be the total potential energy at A2. That must be the total potential energy at A2, which is half of 2k into, let's say, A prime squared. A prime squared. So A prime would be A by root 2. A prime would be A by root 2. So this would be A by root 2. Its leftmost extremity is going to be A by root 2. Right? Okay. There are times when they would ask you to locate the equilibrium position with a mass m connected. That's a very common situation you encounter in exams. It's a very simple way of dealing with these situations. So these are two springs of length 0.2 meters each, and we want to connect this end to this end to this, and we want to find the equilibrium position of the mass m. Right? So let's say when the mass m is in an equilibrium position, the first spring, this spring has got stretched by an amount x1, and let's say this spring has got stretched by an amount x2. Right? And the total amount of stretch in the two springs must be x1 plus x2 must be 0.2. Isn't it? The total stretch in the two springs must have been 0.2. Right, Saurabh? So x1 plus x2 must have been 0.2. Okay. Not only that, this spring will exert K1 x1 on this mass in this direction, will be balanced by K2 x2 in this direction because it's an equilibrium position. So K1 x1 equal to K2 x2, which means x1 must be 3x2. So 4x2 is 0.2 x2 is 0.05 and therefore x1 must be 0.15. Right? Which means the elongation of this spring is 0.15. The original length is 0.2. So which means the mass must be 0.15 plus 0.2, 0.35 from this end. The mass must have been 0.35 units from this end. Isn't it? 0.2 plus the stretch in the spring 0.15, so 0.35 units from this end. This is the equilibrium position of the mass M, right? The original position of the mass M is like 0.3 units. See, this was the original position of the mass M, 0.3 units. That means the mass must have been displaced by 0.05 units. This was the center, original midpoint. The mass must have been displaced by 0.05 units to the right for it to have been in an equilibrium position. From the midpoint, it must have been 0.05 units to the right. Now, one thing, of course, just going a little offbeat, not to disturb the harmony of simple harmonic, but one thing I must communicate, one very important thing in kinematics which you encounter. Can I wipe this off? Right? Just a little bit of a detour for a few minutes. Please bear with me. Let's say this is a missile. Very shortly after the Burdwan incident, we will see all of them flying in the city like chocolate bombs. Okay. And this is a target T. This is a target T. Okay. And this target is moving horizontally with a uniform velocity u. This target is moving uniformly with a velocity u. Horizontally. It's moving horizontally with a velocity u. And this is a missile aimed at the target, moving with a constant speed v, but its direction of motion always pointing towards the target. Its direction of motion always pointing towards the target. That means eventually the missile will follow this complicated trajectory and will hit the target somewhere at T prime. Will hit the target somewhere at T prime, let's say. And I want to find the time it takes to hit the target. One thing, let's say when the missile is here, then its direction, it's pointing towards the target. Let's say this is an intermediate state of the target Ti, and it's moving with a velocity. It's moving with a velocity u to the right. It's moving with a velocity u to the right. So at all times, the direction of motion of the missile is always headed towards the location of the target. That's why this complicated trajectory of the missile. That's why this complicated trajectory of the missile. Now, what's varying is this angle theta. What's varying is this angle theta during the journey. This is constantly varying, right? And let's say the initial separation between the target and the missile was capital L. Now, this angle is theta. This is u cos theta, right? Now along the line joining the missile and the target, what's the relative velocity? V minus u cos theta is the relative velocity along the line joining the missile with the target. The relative velocity is v minus u cos theta, right? This is the rate at which the separation between them decreases. This is the rate at which the separation between them decreases, right? In a small time dt, the separation decreases by this amount. The separation decreases by this amount in a small time dt between the missile and the target. Let's say if t naught is the total time it takes for the missile to hit the target, if t naught is the total time it takes for the missile to hit the target, then the must be sum of all of this must be the total decrease in separation for the missile to hit the target. This is the decrease in separation in a small time dt. In a time 0 to t naught, this must be the total decrease in the separation, and the total decrease in the separation must be L units for the missile to hit the target. Relative separation, right? So the relative separation must decrease by an amount L for the missile to hit the target, right? In a time t naught, the horizontal displacement of the missile and the horizontal displacement of the target must be the same. What's the horizontal displacement of the target? ut naught in a small time, in a time t naught, and realize that this is v cos theta, where theta is continuously varying. The horizontal displacement in a small time dt is v cos theta into dt. V cos theta into dt. In a time t naught, the horizontal displacement is going to be 0 to t naught for the missile. The horizontal displacement of the missile in a time t naught must be v cos theta dt 0 to t naught, right? And that must be equal to the horizontal displacement of the target, right? Which means integral cos theta dt 0 to t naught, as you can see, is ut naught by v, right? And that cos theta dt here I can replace by ut naught by v. When I integrate this first equation, then I get vt naught minus u squared t naught by v equals L, right? And that gives me t naught equal to VL divided by V squared minus U squared. That's the time it takes for the target to hit the missile, and therefore it's important that V be greater than, V has to be greater than, the speed of the missile has to be greater than the speed of the target. What happens when V is equal to U? This will become an asymptote. This horizontal line will become an asymptote. It will hit at infinity, isn't it? When V becomes equal to U, this will actually, the horizontal line will become an asymptote to the trajectory of the missile. That's what would happen, isn't it? Got me? So there are situations where, you know, they will tell you this: the missile constantly changing direction, and eventually hitting the target, and therefore, you know, this kind of a comprehension is a must, right?